Artificial intelligence and machine learning. It's a school of AI. Cool, huh? This is one.
How did you get Princeton AI? Excuse me.
School of AI.
How did you get? Excuse me.
Of okay. All right, now get in there. Go. Just go. I'm in here somewhere. Yeah, let's see. Okay, might as well go to today's class. Or read anything else. Read anything you want. We haven't done anything more.
I went to bed.
This is one of the advanced places. I don't know. I just go to meetings, but I don't really know. See, I didn't sign in, so I'm not on there.
No, we're not going to use Colab today. We're going to try to. I'm good. Yes, the second meeting.
These guys are Joel. You gotta meet Joel.
I recorded it. It's just probably the easier thing is to get the camera angle that's physically on the other side.
Yeah, I'm
I
trying.
remember the other guy.
I brought my GoPro here.
Yeah,
but
he's
I don't know.
Vinicius.
But the audio
Vinicius is the guy from
Just the
Brazil.
video, it's like if you can see over
In
there,
the back.
like Rob right now, it's just
And the guy in
ISO
front
instead of
is high
MSI.
school.
Like I'm trying to figure
Hey,
it out.
Vinicius.
Hi.
I want you to meet
No,
Junior
Hello.
Magan, and he's just flown in from Paris today. And he's doing big data, works on big data.
All right.
I couldn't even understand the CB, it was so incredible.
All right.
But he was really interested.
Making the art styles.
So but he just flew in, so we haven't had a chance to look at him.
You just arrived?
Yes.
When did I pick you up? About 3:30, 4:30?
All right. What are we going to do here?
I would be in time.
At Siemens. He's working at Siemens
Yeah,
on
sure.
big data.
Welcome.
Excuse me.
Yes.
So these guys.
The tour. I never used
He's
this.
been
The Princeton.
The Princeton Library? I think it's the first tab that opens princetonlibrary.org.
So if I have to-
This, you click the red thing over there.
I never use this.
some of these guys. Maybe you can establish a relationship.
Yes. And then princetonlibrary.org.
I thought that would be good for you.
Princeton Live.
Just
you'll
type
have
in
more than
Princeton
just
Library.
being at Siemens,
I think
you'll be able to
just enter now and you can go to the
That's one
website.
reason why I
Sorry,
thought
it's
that might be nice for you to go to
princeton.library.org.
Siemens.
Click that link.
Oh,
They're wild.
Princeton University.
Really interesting.
Oh, can you go back? Princeton Public Library, sorry.
Hey, how are you?
This one.
Good.
Okay.
And then you scroll down and this one.
Just kidding.
Okay.
Just kidding.
That's why you're here,
Thank
right?
you so much.
Yeah, I'm trying to do homework that I should have done 3 weeks ago. These are the people who signed up
Yes.
to work on a very special project.
Yes.
To start speaking. They could get involved.
Yes.
And
Yes. Yes. Yes.
they're putting their, not putting, they're listing how they see themselves in terms of knowledge in different areas. Data engineering, Flask, I don't even know what that is, front end, AI, marketing, business knowledge, and so on. Or project management. But I know business knowledge, project management. And I know zero about the rest, but I'm just not on the list yet. Because I haven't even figured out how to get on those. you were interested.
Do you have the key?
Bottles.
Wait, why'd you buy it? The key works, right?
No, but no. You can never trust the markers.
This is the last school they.
You have to have
and I
your
know
own.
it looks
No, yeah.
totally incomprehensible.
I had two. I bought
Actually
two.
understand.
And then my wife looked at one and said,
What we
okay,
did
that's for a box.
is
We're going to
had
move.
two images.
That's mine.
Oh, you,
So
oh, you guys are moving?
we had two
Yes,
images.
she's going to do
One was
English
the
in
image of a
Philadelphia.
face.
And then we're
One
going
was
to
the
move
image
somewhere.
of,
We don't
of,
know.
of, of
September.
an item,
Close to
let's say,
spring.
an item.
Okay, I was
A
like,
picture,
yeah,
and it could be a dog.
Yeah.
And it was a dog or a person's face.
All right, guys.
And then there was a style.
6:10. Probably we're going to have a few more people showing up, but it's time to start, right?
Right.
Thank you very much for being here again. Just a brief note. I'm a little bit sick, so today's going to be the. Let's try it. That's it. It's going to work well. We have a couple of announcements. Okay, first one. So, last chance for those who want to participate to the building a startup thing, the hands-on part of the course. I've split it already. Everyone who put their names in our spreadsheet into two groups. And we're going to, this week, we're going to, tomorrow, I'm going to assign some stuff. And actually, on Saturdays morning, 10 a.m., I used to hold office hours here. And then I talked to Kelsey, and we're going to change for a hands-on part. It's not a class, not at all. But it's a time for everyone to get together and work on the startup that they're building. Now we have here two teams. Let me ask you something. In business, who is the most important person in an AI team?
The customer.
The
Yeah,
client.
it's the customer. We don't
That's
need,
true. That's true.
it's the customer is the only thing that matters.
That's good. Okay, so who's the second most important person? No, the person who's going to put everything together, the project management. Otherwise, programmers just go crazy with algorithms and do crazy things. They say, no, we can improve that. No, we can go this way. And it's a task for the project manager to say, no, we have to deliver. Come on, fast. Let's finish this. So that's why I input it here, project management. So each team, I place it two. I've tried to put always two people with a good level of skills in any one of the skills, so you can share the workload. Yes.
So instead of project management, do you want to put more of a Scrum Master? Because if you want to do it in an agile way, you don't need somebody who comes from waterfall model. You need more of agile.
That makes sense.
Look, that's true, but I don't think that we're going to enter this. We are not building an actual startup. It's something that is going to be delivered in 2 weeks. So it's something so we can have a taste of what would be to implement an idea.
I think it's based on the style of like whoever is taking control of that specific project. Like if they choose to go in a more agile manner. I mean, it's the time frame itself is really small. So.
Yes.
I didn't sign
Ah, fantastic. When I was thinking about this, I was thinking about it would be perfect in this. All right. So whoever wants to join, the link is in our meetup group. So is there someone here who wants to join and hasn't joined yet? Your name's here? No.
In the initial.
Okay. Fantastic. I'm going to add later.
Maybe.
You can. I don't see mine anymore.
It's if you signed up, it's probably in the initial sheet, not in the group sheet yet. So we'll put it in the group sheet.
Yeah, so just so we can go again, let me get here. If you go to our okay. If you go to our meetup group, Princeton School of AI, you come here at discussions. It's already on discussions. Here's the link. So you just add your name here. All right, a lot of people. And I'm going to add, or maybe if the group is too big, we can divide it into 3 groups, which probably is going to happen. Okay, so what's the project that we're going to build? We were discussing this last class, and maybe so last class I said let's do the transfer learning for the reunions using Princeton style. For those who weren't here the class before, this class we're going to go through an algorithm that grabs a style of one and the content of another feature and merge them. What to do with filters, just like filters. So we're going to do that a web for reunions using Princeton's English or something like that. Maybe we can put some Einstein. Very cool.
It's like mimicking the art style of like these prominent artists by getting like their style and using the content of the picture, and like that's what I said by merging it. So you can have like a photo in as if Vincent Van Gogh painted it or Paulo Picasso. It's based on the style of the artist.
Yeah, so that's why the different teams actually they are going to target the same project, and what we're going to do is to see whose picture the client at reunions is going to download more. So you're going to upload your picture in a website, and then you're going to have 3 choices, and then the person will choose one to put on Instagram. So each choice is going to be from an algorithm of one team. And then we see who's going to win. We're going to see who's going to win. Okay? Yes, please.
So the model is going to be pre-built.
Yes, definitely. Definitely.
It's not when you choose the picture, you're going to go build it there, right? You're not going to do that. We're not doing that.
No.
So,
Otherwise,
all right,
we're...
so there are going to be 3 different models.
Yes.
Got it.
Yes. 3 different models. Already trained, everything.
Right.
Is just, let's put some filters there, and that's it. And let's make this competition. I think this is going to be fun. Okay. And for example, the Einstein idea, let's see what we can add there. The teams are going to decide what they're going to do. I think I should take my name out of that. Okay. Second thing, and very important, those who doesn't have a lot of experience with Python, in May, the Princeton Library is going to have a class in Python. So I have had this request a lot, and so Kelsey is doing a fantastic job. Right?
Oh, yeah,
She's going to.
Kelsey's a technical.
Kelsey is the person at the library
As well?
who does the technology.
It's ongoing. It's I don't know where it is right now. It's going on.
All this stuff. She does this.
The reached Python. It's
There was one
used to
earlier.
attend that. It's not Brian. Dan.
I think so.
Yeah,
Dan. Yes, it's Dan.
he's done it twice so far.
Yes, he had some classes before.
Right.
And in May we're going to have this class again. And so good news. Those who doesn't have a lot of experience with Python, who are struggling with Python, we have this class.
Yep.
What else? Okay, so Saturday, 10 a.m. one of these glass rooms. We're going to start the hands-on part. Questions? Comments?
Thanks for the future.
Everything's free.
And by the way, for those who don't know, Kelsey is the library technology program director. It's like really good. Helped us set this up.
Okay, now. Today we're going to go through that code. So until now we had everything on Colab, and we are going to keep trying to do that with everything on Colab. But there's a very important thing for you to understand. The models for 80% of the things that you're going to think of already exist, and for free. So it exists already. And it exists in this place called GitHub. So whoever doesn't know GitHub, please, you have to start using this page. You're going to, you search for an algorithm that's going to make some prediction, that is going to do something. And basically, you just clone it. It's going to be in your machine. And then you can do your own, you can actually do whatever you want with that. That's what we are doing here. Why I'm saying this? To build an AI startup, remember that it's all about having the MVP, the minimum viable product. And for that, you don't need a lot of money. You just need something that you're going to present and try and see if there's real value on your value proposition, on the thing that your thing is going to sell. Now, you don't have to hire a guy who's going to charge you. A data scientist nowadays is what, 150 at least. So it's pretty expensive, So you have everything on GitHub. If you know how to use this, it's a fantastic tool. So for those who here doesn't know how to work with GitHub. Okay, so that's good. Later we're going to go through a course on that. Whoever wants to clone this, we're going to go through this exact code. So it's how to do style transfer in TensorFlow. By the way, this is a Suraj Raval's one of his videos.
He's the head of the Princeton School, like not Princeton, sorry, he's head of the School of AI, like director of that. We're kind of just sub branches in multiple cities across the world. So.
And what's his name again?
Siraj.
Siraj.
S-I-R-A-J. It's not.
Siraj?
Yeah, S-I-R-A-J.
Yeah, I got it.
R-A-V-A-L.
Is that I source I?
I think it's the apps, like the bar, like the vertical bar.
The vertical bar?
Yeah.
It's an L, but they're L's.
Oh,
Okay, so.
this guy.
See the YouTube guy you told us about, yeah.
Yeah, that's.
That's him, yes.
Is that cool? Isn't that cool?
If there are any particular questions, not all the content, but some of the content that we do are from his videos, like this one. So his videos are really useful if you want to go into like a completely different topic, like reinforcement learning, which we haven't touched on now. His videos are really informative and useful on that stuff. So it's definitely worthwhile spending some time with it.
It's not copied onto the
Does he-
School of AI.
Does
No, I don't.
No, it's not on Princeton School of AI GitHub. Okay. It's on Suraj's GitHub. I have your picture here. Let me change the picture. Just a second.
I just want to ask you,
Yes.
I am new, so instead of going that different GitHub, etc., how about if set up my own big data server like Spark, Hadoop,
Yeah.
and then in Promise, I set up my own data using that tools and not going to the GitHub, and training set up training set. For instance, if I want to use a deep learning CNN, so I have to get my MH and then train my second layer of that's gonna be my input, is correct?
Yeah.
Okay.
And then train my model and split them to the training set and test and validation.
Okay.
And then using back propagation and find out how is my model is working. Definitely, I need some kind of tools like activation code, whether you're going to use activation sigmoid function or modified or other tools.
No, you're right. And for the building the model and stuff, we use either TensorFlow or Keras. But the whole point of using GitHub is so the code is easier to access, because the data and stuff for this class, loading it isn't really the problem, because it's like a couple of lines and we load all our data. We're not like explicitly downloading JPEGs. Like in some, like for example, the last class, I just ran 3 lines and I got all my data. But for like setting the activation functions, building the model itself, we use Keras, but we use GitHub. So the code.
Google Keras.
No, Keras is separate. Google TensorFlow is different. Keras is like an API, like a wrapper on top of TensorFlow. It's basically to do what you're saying.
No,
Like,
let me just complete my suggestion.
okay.
Now we know that Azure, Microsoft, AWS,
Yeah.
they already have EMR, for instance, and they have instruction using how to get high. So why should we go also all this complicated situation?
But we're not running it on an Azure server though. We're running
Not Azure, maybe
like,
AWS.
we're not running it on a cloud server like AWS or Azure or like Google Cloud Platform. This is either, that's what he was talking about, Google Collaboratory. We're either running it on Google Colab, which is like an online version of a Jupyter Notebook, or we're running it on the computer itself. So we don't need to go to Azure and then go to GitHub, because we're not really running it on an online cluster. We're just like, the whole point is to make it easier to get the code from your end, because like there are other, like we could share it physically, like, send an email to everybody, but like getting it via GitHub is a bit easier then. So you can just download it, it's faster.
And you know what? Your writing code is going to be time consuming. They have already prepared Lambda function, for instance, serverless server. You can easily.
GitHub is a source control system. It's not a database.
Yeah, GitHub is just to
GitHub
get
is for source.
Yeah, it's so you can get the code itself. We're not to be honest, we're not really dealing with like a lot of data itself. We're mainly building the models locally. The whole point of GitHub is so you can just copy the not the data, but the code, like the physical like lines of code onto your computer. That's the only reason we're using GitHub. We're not putting our data in GitHub. It's not a big data server or like a code server. It's just to put the code on there.
Okay, your choice. But I suggest using these tools make life easy. Even MATLAB has a lot of codes prepared already. MATLAB, free.
It is LL.
Yeah, it's just it's definitely a technology stack. You're right. We
How
could
to
use
do
that.
transfer learning.
We could explore doing it in AWS, but since it's easier to run it on the computer, we're not going that way. But definitely, we'll consider the suggestion.
Thank you.
Good. Can you show us what, again,
Yeah.
that GitHub address?
The GitHub. Yeah.
Or can you copy it to the Princeton School AI GitHub? We are already connected to it.
How should you spell it? Oh, okay.
How to do style transfer?
I just want to. I have explained, I teach these courses. And if you will use this is really good.
Had the chance to download to get to clone the directories to the environment. Has someone cloned the GitHub?
Did we
Okay,
reach the
we can do that
GitHub?
later.
On this memo, right?
I'm sorry?
First step is to call this.
Well, if you want to, yes, it would be. It would be. If you want to put your images, etc. Do that. Yes, ma'am.
If we download it locally, then how do we upload it into Colab?
Colab is we are struggling with the structure of Colab because, as you can see, you have here different files, and in Colab
To
we
where?
haven't figured out how to create an
That
internal
is
internal
just how to go to
environment. So basically, when
Search up how to do stuff.
we were doing everything in one script,
Right.
right? So let me enter here. Colab.
To do.
Okay, so
How-
this was me trying
How
to put
do
everything
style
on Colab.
transfer.
Trying to get this code and inputting everything on Colab. My problem was I didn't have time to do that, but I put a lot of effort on it.
TensorFlow.
Still, I have to learn how to create an environment where I can have the model. For example, this file here,
FLO.
pgg16.py, this is the model already trained. So
FLOW.
that's the.
FLOW.
I don't know how I would upload the already trained model to Google Colab. Cool, for sure, there's a way, definitely. I just don't know.
There are articles out there doing it in Colab.
I ran a few, unfortunately, doing setting up an internal environment at Google Colab.
Is this the code that you use?
Yes, it is.
You use this?
Yes, this one. Okay, let's go. Okay, so just for
And then he's just gonna. Did you show how to clone it or is it just?
okay, so here to clone this so you just click here, clone or download.
Save. You can save one.
Clone it.
So hang on. Put that code in.
So, but most people knows how to.
Yeah,
use
most
it.
people, that's true. Yeah,
Everyone knows how to use it.
Yeah. Did
That's why I asked.
you explain the problem with the Colab thing because the image is loading?
Yeah, that's the point. We
Yeah.
don't know how to make images at the Colab
Yeah.
or files or etc. Yes, please.
So I just open the GitHub repository, and browse to that file, and it opened it from Colab, and then I did a file save as.
Oh, but we're not using Colab right now, so therefore you can't do the file download as thing in Colab because like we're using physical images to do it, and in Colab we can load the individual files onto like that server cluster, whatever we're on. But creating a new folder called images and putting those files in there, that's kind of a problem. We're just still figuring out the Colab
Okay,
part.
yeah, so I did figure out a way to point it at my, to mount my Google.
Okay.
But,
Yeah.
Then we can go
Then
through
we
that.
can if that's a solution, then that's great. Then we can just put this on Colab.
Just gotta get.
Yeah,
I
it's
gotta get the images on there.
yeah, get it.
But I could do that through the interface,
Okay,
once I get.
sure. Yeah, we'll just like talk about that once it's done because like that's a smart idea.
Okay, so just for what we're going to do is we have an image.
I need to send
We have an image that we like the style.
If you skip
And what we're going to do is to merge these two
email
images.
notification.
So you can see the contours here, the
Willy Wonka.
the lines
So maybe
of the content image and the background of the second image. That's what we're going to do
I
today.
don't want you to lose this. This is the most
Okay?
important. There's the style,
Can you,
and that's how they put it.
are you gonna go over
It's mixed together.
the
This is what I'm
process
asking.
again? How, because it's running two different gradients, right? You have one image that you have to go through and trace. Then the confusing part is where that stops and the other one comes in and has to merge it.
What the heck, I'll just-
Right?
Yes.
Okay, you're gonna go.
Yes. We're going to put we have two loss functions, one for the content image, one for the style image. And the gradient actually comes from the combined loss function. So
Sorry, it compares the mixed one and like the original one, the content one, in order to find out like it's just matrix multiplication to reduce like the difference between your combined one and your original content one. That's what's going on. That's a combined gradient loss function that he's talking about.
It doesn't take your original image and do first. I thought it does that first. And establishes your.
There's a regular taking the layers out. You're right. Like just extracting the features from the content. That's the content part. And then when you're merging them together, it looks at the merged one and compares it with the content one in order to find out like how different they are. It's called a Graham matrix, and you do the multiplication of that in order to find out how similar the content one is to the mixed one. And you want to make that similarity as close as possible. So all the contours, like the contours of the shape of Willy Wonka, those are clearly identified, while the style still exists. So that's what's going on.
Yeah.
okay, so what we're going to do, we're going to select some layers to deal with the style image. We're going to select other layers to deal with the content image. And actually, in this algorithm, he selects the same layer. He grabs these two layers for the style, and he grabs this one for the content. So you can mix both. This model here, the VGG16, is already trained. So the weights here, they are already established. So what I have here is a very good model to recognize images, already trained. What we are going to do is to grab these layers for the content and the layers for the style and change a little bit. We're going to train in our image, we're going to input this one, and we're going to try to make a prediction. He's going to, using only these layers, he's going to make this some sort of mistake. And then he's going to update only the weights of the layers that we're going to select to get as close as possible to this one. And the same thing, other layers are going to be responsible for the style image. So I'm going to update this guys here based on the content image, and these guys here based on the style image. And then in the end, so these guys here, they're going to be responsible to put these characteristics, and these ones, they're going to be responsible for putting the lines. Okay?
To extract the content, just like this is something we talked about, not specifically for this case, but about CNNs in general, like the class before that. And it's basically you want to, like, the more and more like the hidden layers that you go through, like the more and more abstract the features become, like how we were talking about, like the straight lines and like, the curves, etc. So the extracting the content is what's done. We have like a neural net, the convolutional neural network, which actually extracts the content. That's how the CNN works itself. You're trying to abstract it in order to classify the image into whatever categories if you're using a CNN. But in this case, we just want to get the abstracted features of the image out. So that's what's we're using the CNN for the first part.
Questions so far?
Process, I think.
I'm afraid that I'm gonna interrupt you, but you said it's a good algorithm. The way we evaluate algorithm, calculate the cost function based on weights and bias.
Okay.
How do you know this is a good function?
No, this
Good
is
algorithm.
the VGG16 is a non-algorithm already. It's already pre-trained. It is something that it has been used to deploy solutions.
Yeah.
And it exists. So we have papers that uses these algorithms. This algorithm that we're going to use. So it's pretty much established. And that's the point of this class that I was telling you.
Okay.
We are going to use already trained models. The class in May, we're going to start to build our own. But right now, we are going to use things that are it is already known to be a good algorithm. Of course, that in 10 years we're going to have much better algorithms. But nowadays, this is one of the best on image classification. It's very interesting, the VGG16. VGG16, check this out. Put on
It's very important, very important. If you don't mind. The way I compare algorithm, I have to calculate my cost function or error function, and then calculate what is the gradient of each neuron, and then ended up some number like n or
We're going to
log
go
of
through
n.
that. We're going to have that because we're going to compare this image to the image that the algorithm, a given layer that we're going to select is predicted. We're going to compare the results, and then we are going to retrain to diminish this loss function.
Thank
We're
you.
going to do that.
Thank you.
Okay, so let me see.
Where's the mouse?
We found it. Let me see if there's something that I would like to go to. No. All right, so VGG16 model.
That's the imports just a bit earlier, the functions that we're
Okay, so we are importing we have a class of this guy is already trained. Remember that file? In the GitHub, that's the file, we are calling that file. And we are building the model. This is the model. Now this part, that's the important part. We are going to say that the fourth layer, let me show, oh, here it is. Those are all the style and the content layers that we're going to use. So for the content, we're going to only use one layer. While for the style, we're going to use many more. I think 14.
Just one thing, you may wonder why we're not completely training a new one, but the thing is, this problem, like you can just fine tune like the layers itself from the VGG16 like model that we have before the pre-trained model, because that's been tested and proven to be a very, very good model. The architecture and the weights that it's trained on, it's based on the similarity of your use cases, like based on how similar your use case, your data that you're using now is to like data that it's been trained on. In fact, you don't need to train a brand new model. You can use something that's already loaded for like faster times and efficiency, etc. Yeah,
You can grab a chair outside and then.
okay.
Okay. Yeah, so this part is important. You see how many convolution layers they have. So I'm not going to go through again. How many people want me to go through again? What is a convolution? How does that work?
CNN.
Sienna. All right.
There we
Yeah,
go.
now I'm proud. Right. That's good. We had two classes only going through drawing the matrices and showing the flashlight,
Structure
etc.
there,
All right.
and then they multiply it.
Okay.
Factor.
Now moving on.
It's hard to describe it. It's all in this. it's
Oh,
all-
this
it's
function's
all on the
here.
website.
They are only to get the that's to
But
deal
it
with the
replicates what
image
this is.
itself.
This is the shape.
So they are
This is
helper
part of the
functions.
picture. This is part of it.
Remember that. That's very important. We don't have a reason.
Yep, I'll just get the key.
No, please do. Thank you. What we are doing, whenever you upload a picture, it's very important to know the size of that image, because the size of the image is going to be highly related to the size of the filter of the flashlights that you're going to go through, the convolutions that you're going to go through. So whenever you are in a real application and you go to Google Images, you download a bunch of pictures and you say, okay, I'm going to have an algorithm, I'm going to make a prediction, that's it. No. This part where you're going to load the image and reshape the image is very important. They have to have the same structure, or at least they have to have a similar structure. Usually that's I have a big picture here and a small one. The same picture that is big and small, I'm going to show you later, that because of let's say that you have an image that is this size and another one that is this size. And then you have your flashlight like this size. You're going to train your algorithm to make changes here. And then you're going to move to the side a little bit. Then you train your model. If you put the same thing running here, you're going to change only only a small fraction of the pixels. If we are trying to do a style transfer, this is not going to change much. We're going to change a lot of things here. But as it is just a small amount of pixel, the final picture doesn't look good. It looks, you can see the pixels that it changed. So it looks like each one of these guys, they are independent. It looks terrible. So it's very important to you have a bunch of images, reshape everything, put everything at the same size or at least a similar size. Okay?
Is there a ratio that is ideal?
No, because actually, depending on it will depend on the case that you want to use it. Now, if you are looking into a given situation where you need high quality internet, you need high quality images, you will have to go with the big one. So you need big images, and then the size of the convolution, remember that we can decide this. We're going to make it bigger. So you can grab the style of one picture and change the other. Okay?
You have to fine tune it. It's a hyperprinter. So
Okay, so there's a certain amount of trial and error.
there is definitely
For
a
the
certain
size
amount.
of the
Yeah,
photo.
yeah, exactly. There is some, but
Remember, everything is. There's an economist, an American economist, who says that deep learning is not a big thing. Actually, what you have is M large enough. A lot of people making mistakes, and then one do something great and say, "Oh, there's a methodology. My methodology is better." There's no methodology for deep learning regarding this guy. Well, according to this guy. So it might be true. It might be true because everything is very. How do I say this? It's a hand job.
You know, you gotta get your hands
That's not good.
you
It's,
gotta get your hand dirty while like fine tuning the.
There's a word for this. I know in Portuguese. Artesanal. Craft. Okay. So yeah, so we have here, we define a load function. So you can load the image, save the image, and of course, you have to plot it. But those are help functions. We're not going to go into details.
It's like visualization stuff, so you can just
All right, now, loss function.
Yep.
In our case, we're going to go through with the mean square error. What is going to happen? We have one picture. We're going to have the output. We are going to get the values, subtract, make it square, sum everything, and this is going to be our error measure. So, is there anyone who's not familiar with mean square errors?
It's
Who's
just
familiar with mean square errors? Okay, so
the notation may seem fancy, but it's like a really, really basic function, like just basic squaring it. So
the loss function is one hyperparameter. You have several. that you can choose, and each loss function is going to end up with a different result. It's going to tune differently the model so you can grab certain patterns differently. So let's say that I'm going to make a first a very a simple example. You have here 2 and 3. This is my x. So let me check. I have an image 0, 0, 1, 1. What is this image? You have here, the image is something like that. In this case, it will be something like that. Okay? So this is the image that we see. This is how the computer sees it. Now, let's say that we put this image in our algorithm and it outputted 1, 0, 1, 0. Basically, what we would see would be something like this. Okay? So it's not the same at all. How the mean square error would capture that? It would make 0 minus this 0 minus this 1 plus 0 minus 0 square plus 1 minus 1 square plus 1 minus 0 square. Okay? And that's 2. Does that make sense? Yes? Questions regarding this model? Don't be shy. No? Okay. Good deal. So that's mean square. Basically, what we are doing is doing this, but name. That's what we are doing. Okay, that's this function. So regarding the programming, we have here the TensorFlow has this reduce means. So basically, we have our input A minus the prediction B. We're going to square this difference. That's a TensorFlow operation, and then we're going to reduce this mean.
And it's
basically you're summing up.
It's mean squared error because you're dividing by the complete number of data points.
Okay.
Say that more loudly, please.
It's mean squared error because you're dividing by, you're taking the average, like all the error throughout the data points, like 2 or 4. So it should be 0.5.
right.
That would be the
That's right.
squared error. There's also some squared error, which is if you don't divide it, you just add it up.
Now, interesting things to understand regarding mean square errors. Why we had to square it instead of just using 1? Please.
So basically, you like to see what is the difference of your actual value and predicted value. That's the one you are doing.
But if I were to do this, wouldn't I capture something similar? Or at least, let's say that I put module here. So every error is positive. If I do that, I would also see the difference between what I predicted and what is the actual value.
Well,
Right.
another way is it's called square error detection. Instead of mean square, you can say error square
Yes.
detection.
But we square it, first of all, not to use module, but mainly to make a lot of, whenever you make a big error, you're going to punish a lot. So in this case, let's say that we only use absolute errors. Let me do a different graph here.
The worse you are, you don't want it to be linear. Like exponentially, if you do really bad, you want to really get, the model really wants to get punished. If you just do like this absolute value, it's just a pure linear trend. While we want it to be exponential. So the worse you are, the much higher the punishment.
Okay, that's perfect, because this guy here, you see it, that's a small error that I made, and here is a huge error, correct? If I were to use the linear one, this would be the value of the error, and this would be the value of the error. Now, if I square it, it's going to be
Up there.
way up.
That what Garris is using? Are you taking the square root and where the error is given?
No, not this case. No. I don't think so.
You don't think so?
Yeah. It's not. I don't think it's root mean squared.
No,
That's
this would be another. This would be another possibility. There are some chairs over there that you can grab. Don't worry.
Okay.
I'm getting uncomfortable. I'm going to get chairs for you. Okay, so questions?
On error calculations, what we're doing here. Thanks.
So that's, yes, please.
So why do you choose square rather than cube or quadratic or linear?
That's a very good point. And I don't know if it was clear here. First of all, everyone uses it.
Used
But-
to be easier math. too.
Yeah, everything for that is better. But actually, the power that you pick is going to change the output a lot. So this is another hyperparameter that you can play with. Now, if you put let's say to the power of 16, this guy here, he won't care for this guy. He will care only for these guys here. So if this error is not important for you, you do that. Now, it might be the case that this error is important to be captured. Then you reduce a little bit. If you want, okay, I was playing with a big data. PGA is golf, right?
Yeah.
Okay. And I had the players and I have their stats. And I was playing with them and doing some predictions regarding how the player plays, what's going to be the prize that he's going to win in the end, or how successful he's going to be. But there was one guy there who simply, how do I say this, crumble, this was in my way, let me put this way. There was one guy who is this guy here. Who is this guy in golf? That is was making my predictions terrible. Tiger Woods. So if you want to capture only Tiger Woods, you would do that. If you want to capture the structure, the common error structure of the model, you do something more like this or square. So squared would be something in between. Was that better? Questions, please. We're good? All right, moving forward. The hardest part is the mouse. Okay. Oh, now the things get interesting. Okay. Now we are going to create the content loss. So we do have two images. One is for content, the other is for style. We chose beforehand in our model the layers that are going to be responsible for the content and the layers that are going to be responsible for the style. Sorry. These loss functions are going to be different. This one for the content is going to be very simple, very simple. So what we are doing here, let me scroll. Move on. Okay, I'm starting a dictionary, and then I have here the layers that I'm going to use for content. We have defined it here, at the top, that here, the content layer is going to be the third one, third convolution layer. Actually, the layer number 4, the fifth layer, what is the third convolution. So we have only one layer. The nice thing about this algorithm is that it left open for, if you want to increase the number of layers, you can. It's just change there and it's going to work. Okay? Okay, so whenever I'm calling this function, I'm going to activate these layers, and this dictionary that I created is going to be fitted on this section. I have here the model already built. I initialize the losses, and here I'm going to have a loss. The loss is going to be the value and the layer. So the layer output and the value, what I'm calling the value is the image. The value of the image, the numbers. So I have these two things. I have the, how can I say this? It's not good. So I have my original image that I'm going to input. And that session.run is going to run the session on the image and make some prediction, grab some information there. And this is going to be the layer. And I'm going to make my loss. I'm going to create my loss. And I will have a lot of losses. Right? I'm going to make a series of losses. I'm going to have a list of loss only for the content. Only for the content. Is that clear or not? Okay, raise your hand who didn't get it.
Who did get it?
Who did? Yeah. Okay, I have to say who did.
Yeah, who
No,
did?
the problem, okay, we had this discussion. Whenever I say who did, everybody raise their hand and I cannot see those who didn't. That's the problem.
All right, so why just for the content? Just say you just.
That's first. That's we are only looking for the content right now.
Oh, you're only doing one layer?
The model chose that way, but actually this function is set. If you want to increase, you just increase above. Remember that I put just 4?
Yeah.
You can select a bunch of them, and that's it.
But it's going to do the mean squared loss after each layer. Or after the whole thing.
After each layer.
Af-
The loss functions can be weighted differently for each and every layer. So like the loss functions are per layer, and then after, like based on
That's
the
true.
layers you choose, they change.
For each layer that I pick as a layer that is going to deal with the content.
Yes, exactly. For
Not
content
the whole
layers.
model.
Only for the content layers, because we're dealing with content right now.
Okay.
So since we picked like the third convolutional layer, it's only going to do it for that layer. But if you pick, more 4 or 5, you could it's per layer it calculates the loss function, like how bad the layer did. And you can have you can even have, it says it right there in the blurb, you can have weighted loss functions for the different layers. Obviously something that can be explored.
Okay.
Like a bias, like how human setting that.
I'm going to read this. Yes. So we're going to input one image. The layer is going to make a prediction. We're going to have a loss of that. This loss we're going to append into our loss series. In our case, we only have one layer. So it's only one number. In this case, for the case of the style image, it's going to be different. So here we have one loss. We put in the image, we made the prediction, saw the difference between prediction and the actual value, and say, okay, this is our loss. Is this better? Yes? Okay, moving forward.
This is all very, very similar to the content that we discussed the last 2 weeks, like the whole convolutional layer abstracting the information. So
Okay,
that would be a good review.
I'm going to get here soon.
Yeah.
I'm just going to say this. Looking for the style loss is going to be the same thing.
Just, you discussed very nice, thank you for your teaching. In order to improve, how about that in CNN using back propagation and correcting my mistakes error? Are you gonna talk about that?
We're going to use back propagation. We're going to do that.
We talked about that earlier, like using backpropagation to see where the errors were changed. Not in this class, in the last week's and the week before.
Yeah, because you know what, I was just reading one of the greatest programmer of our century, Donald Knuth, Knuth. He said, is not the issue going to the complex algorithm. You can think, use your brain, come up with a logical function, for instance, and you can do instead of n squared or n log of n in simple constants. And he wrote a paper, it's called BDD, Binary Decision Diagram. And he used a back propagation. And I think you discussed this one. We can improve our error very much.
Yes, that.
I definitely appreciate you're doing a great job. You know, I mean, hopefully I'm not interrupting your teaching.
No, we're going to get to the back propagation part. It's going to be in the end. I'm just creating the loss, because what is the back propagation? It is a series of partial derivatives that you're going to grab this loss function and you're going to say, okay, I have to change my numbers here, my weights here, to capture this error.
That's exactly, thank you.
So this, we are looking at how we are defining the error right now.
Exactly.
And then we're going to say, okay, we define the final error like this. Now, how can we update this process? We're going to get there soon.
Thank you.
Thank you. Thank you for that. Now, the style loss is the same thing. The same thing. You can see that you're going to have you're going to initialize the dictionary. You're going to have the layers that you're going to use to make predictions. This gray matrix we are going to go through right now. But in the end, you're going to have the mean square error, and you're going to append in your layer losses list. Okay? It's the same thing. What is different? Now, let me go back. And that's the beauty. Well, now we're going to see what if you were to ask me, okay, what's cool here? What's different? I'm going to show you right now. We have this, the content and the style images, right? Why isn't this algorithm capturing the style of this image and the content of this image? Yes. What we are creating differently that is going to get these contours here of this image and get more or less the shape of this. So that's the true question in this algorithm. The rest is just create the loss function, do the gradient descent, train it, split, train, test, validation. We're being recorded, so it's the same thing. So this is what makes this algorithm different. It's the way that you define the loss function. Now, the beauty is, for this one, we just saw, you're going to simply look at the image, look at the prediction, we're going to make a comparison, right? For this case, we're going to do something different. We are not going to look at the image. We are going to look at another image, the relationship between the pixels. So that's what we're going to construct now, the gray matrix. Yes.
This is where the linear algebra stuff comes in with the multiplying the matrix and like the vectors and stuff like that. This is why we asked to have some basic math knowledge. Yeah, right there.
So let me do this. This works. So in a very high level, and actually, here, look, all those ideas, they are not complicated at all. They are actually smart ideas and simple. You have a matrix, which is your image. You can think of your image as a matrix. That's pretty straightforward. And what this algorithm does is to make a matrix multiplication between the transpose of the matrix and the matrix itself. Now, it's not the image. We have here an image. We are going to make the transpose of this image. Let's say, oh, I think this one's not entirely like that. And I'm going to make the multiplication. This will end up with something that, whenever I multiply two matrices, the matrix by its transpose, I'm going to get the patterns. My pixels are now an interaction of this pixel with the rest of the image, with the rest. Now that's the difference here. So whenever I'm multiplying here, linear algebra, this first guy is going to be this first row times this guy here. So actually what I'm saying is I'm grabbing the top of the image multiplying by the vertical.
The column. It's
The
yeah,
column,
the transpose function is just
But
the matrix.
Dot product. It's the same.
it's a dot product by the transpose. And that, so you can see that instead of getting this first guy here, instead of being just the first guy, is actually this top relation here. And so on. Everything is going to be the relation. Now we are talking about, you're not grabbing the image itself, you're grabbing the style. And that's why. No. Okay, Vinicius. Why don't you multiply here by 2? You can do that. It's not going to do much difference. But let's say that I do this. This image plus itself times this guy here. It's another way to grab the style. Probably in this case, and if I do this a lot, I'm going to grab the content of the first image. Let's say that I do this 1,000 times. So whenever I multiply, this image is going to have a huge weight. And it's not going to change that much. It's going to change anyways. So this is one way to define style, one form. And that's what makes this algorithm so cool. Because instead of looking at only the content, you're looking at the relationship between the pixels. Please.
It's actually going to say the same thing that you were going to say. It's between layers, analyzing what's similar throughout, what is fundamentally similar throughout the layers of the features being extracted for the image. Like if you have multiple layers, like the similarity between each layer, what's so similar, and that's how it extracts the style. It's like what features are shared as you go layer to layer. Like the style is basically, so the content. All right, so quickly to explain this, in the content you're extracting the contours of the face, or like the basically the fundamental features, what makes a face a face. But style, it's like over the course of layers, like what is similar between all those individual layers, like how are those similarities identified, and by using those similarities between the layers, that's a style, because the style is what's shared throughout the features. No matter if you're identifying straight lines, like the curvature of the eyes, the style is what's shared throughout each and every layer, and that's why this function works. It's throughout multiple layers. That's why.
So, questions, please.
So is there a loss?
Yes.
What's the loss function for the result?
That's-
Because you have nothing to compare it to.
No, I have this. I just multiply those guys, and I have one image that probably is a very ugly one, but it is one image. Now I'm going to put in the algorithm that is going to make a prediction, and I'm going to compare this with this, and I'm going to make modifications.
So you're comparing the output of the algorithm with the result of it.
Yes.
Somewhere you showed you picked an array of loss area. What was the purpose of creating the loss?
I'm sorry. What's the question?
In here, you were calculating loss rate and then appending it to
Okay,
so how do you plan to use that?
that's how do I plan to use this loss? Yeah, so that's what we're going to do next. Now, we do have a lot of losses. We have the content loss, we have the style loss, and actually this algorithm even puts a third loss here.
It's about creating the combination of the images.
So it creates this denoise loss, which will be a third one. But what is actually cool is this one. The final loss is going to be a combination of the content loss and the style loss. Which combination? This is something we can play with. If you have the weights of each one of the losses, if I want to have an image that has a lot of style and not much the contours, the traces, I can put this parameter higher. If I want an image that is going to have more content, I can put this higher. Now, this is something that we can work with. Questions? So, okay, now let's see, style transfer. We're going to input the content image, the style image, the content layer IDs, style layer IDs, the weights, the number of iteration step size. Do we remember what is a step size?
It's just while training the model, the cost function. You guys remember like how we have you have the parabola, the cost function, how big of a step that you're taking to get to the minimum. That's what the step size is. Like we talked about the early NLP session itself. Like when you have a parabola, like how big of a jump do you want to take in order to get to your best case scenario, to your global minimum? So the best combination of weights, so you have the smallest cost, or the smaller. Obviously, the smaller the step you have, the longer it takes to get there, but the bigger step you could skip over the minimum. So it's just a hyperparameter that was set.
So your point is getting to the local minimum.
Preferably global minimum. Global minimum would be best case scenario, but for starters, just
Exactly. So we are looking for global.
we want to get to global, yes.
Yes.
So this was related to your question. We're going to have a loss, the combined loss. The way that we combine, that's something that we're going to decide. But we have the final loss, which is the sum, which would be here. And what we have, that's the beauty. At this point, we know the activation functions. We were the ones who put it there. We're going to make the partial derivatives of each function so we can grab the how much will I have to change this to capture this loss in the end. We went through that last class. Remember the partial derivatives? So what I'm saying, if I know partial derivatives, what I know in this simple graph is more or less the inclination at the point that I am. Remember that I don't know this. I know only the point and the, how do you say this, the inclination? The slope, of course. And I know the point and the slope. Now, here we decided to have a step size 10. This is something also that you have to play with. Step size means, okay, I'm going to move this size, move to the side 10. So I'm going to multiply this by 10. I'm going to come here. If I put this too high, so here I'm going to, next I'm going to be here, and then here, until I reach a minimum. My goal is to find a minimum. Another thing is how to find the global minimum, but that's a different thing. I'm trying to find the minimum. If I put the step size too high, I'm going to end up here. If I put too small, it's going to take forever to run. So this step size is something that you have to play with. It's very simple. How do I reach the global minimum? Whenever we start the model, we start with random weights. So we are in one situation, would be like here. Let's say. We have the shape, we don't know the curve, but we know this. And we are going to reach the minimum. It would be here. But I don't know that this is the global minimum. What I'm going to do is to rerun the model, but using different random numbers. Let's say I'm going to start here. And then I'm going to do everything, I'm going to reach here. So, opa, this minimum is higher than this one. So far, this is the global minimum. And I do this several times. I'm going to find a bunch of minimums. And here is going to vanish, which is not good. And you're going to say, okay, I was right at the first time. Yes.
Another way of finding the global minimum is sort of do a grid search, but that's not done in TensorFlow, just using random numbers, random starting points.
How would be a grid search? It's not the same.
Well, a grid search is where you're looking down specific location in a two-dimensional grid. You look at every little point.
So I would go through everything here, and I would find, but it's impossible because it's a continuous function. I would have to go through everything. I would have like a grid. I would have to have a step size because the computer doesn't understand continuum.
Well, I'm not sure exactly, but in Keras, cross validation, take you know, if you exponentiate the search, so you put discrete values in the try on it, but you try it, you know, in powers of 10, so that you're not like moving a little bit, you know. It wouldn't make sense. You get fired or whatever by the time of the thing, right? You know, take powers of 10 and go up from, you know,
Well, in the end, it's the same
to the
thing.
power.
Well, more or less the same
And
thing.
then, but it's, I think, in Keras, it's exactly cross validation.
Let's check.
know how to check on that.
Let's discuss that. Let's discuss that. That is an interesting point.
Excuse me. What was you mean by cross validation? Please.
Cross validation is when you cut the sample off into
Gotcha.
chunks, and you have the training and the test, and it does it multiple times. And so, you can do that in Keras. Set up, hyperparameter. I'll look at the code when I get it all.
I think the major point of cross validation is that when you have a higher variance and lower bias,
Right.
you have to adjust them. I think this gentleman mentioned about that
It's a function of the number of parameters.
that loss function. He said correctly that activation of the higher layer should be in such a way that this similarity of the content and style should be matched similar to each other. I think they are correct, in my opinion. You did,
Oh, I'm
right?
sure they're correct.
He mentioned about that one. I think it was, I agree with you.
No, you're, yeah, that makes sense. Anyway, just quickly to overview this, basically,
Good job.
thank you. Basically, not confused with fancy terms or something, it's just, the data is just taking the slope of the point tangent to that specific line. So now, obviously, there are loss functions where you can give like a given step size and move on. But there's been a lot of research in here. Even in Princeton, there are some professors, they're setting up like a lab with Google to like determine this whole optimization function scenario. But like one uses momentum, like how big of a jump, like I just put M as like a slope. It's a really big negative slope. Then it goes smaller and smaller and smaller until at the minimum, at the bottom, you get like a slope of 0. This is obviously like, I'm talking like the perfect case scenario, not like never, ever, ever just a perfect parabola like this. But based on how much your cost decreases for like a step size, like it basically uses momentum on how much your cost decreases based on your step size. So as you go smaller and smaller, closer and closer and closer to the minimum, you take smaller and smaller jumps, or like the step size gets smaller and smaller. But in the beginning, the step size is big because like you see how much the slope changes in order to find how big your step size needs to be. This is just some advanced optimization function algorithms, but the main point here is to use like the delta slope in order to find the minimum, where the best, if you think about it as dials, like 10 dials or something, well, the 10 dials are the perfect combination that you get the lowest weights. That's what you're tuning the dials, that's what's going on. All right.
Well, is this because the code that comes from Siraj, you use TensorFlow instead of Keras?
Yeah, this
Is this from Siraj?
This is Siraj.
Keras is a little easier to
explain.
read.
To be very honest, we're not going through the code actually, right? We're discussing ideas here. I think that's the most. We're next class, but later I'm going to get that next class. But yes, Keras is the best way to go. Yes, but now we have TensorFlow 2.0.
They claim that they've really subsumed Keras into it.
And it has a tf.keras.
Yeah.
It's simple as that. It's
Supposed to
beautiful.
be the best of both worlds.
And it's beautiful because now you don't have to run the session, everything, so you can see where you made a mistake.
And
You
it's
can
still
go
in-
step by
still in
step.
alpha.
Sorry?
And it's still in alpha, right?
Yes.
There may have been new releases, obviously, I mean, I haven't been completely in touch with it, but there may have been new releases to TensorFlow 2.0.
Yes, please.
I'm not sure.
I just enjoy. I have another group. All right. See you later. How can I see you?
Have you signed up for the meetup? For the meetup group? So reach me there. We can discuss.
Thanks. I enjoyed. Very nice.
Thank you very much. Okay, so let's finish. We're almost in the end.
Final stretch.
Final stretch. Come on, guys, just a little bit more. Just a little bit more. Now, so we are inside this function, the style transfer function. Finally, we're going to call our model. Then we are going to have our session. We're going to start our session with the model embedded. we're going to define the content layers. Those are the layers that we are yes, so that for the extracting the content information. Those are the layers that we're going to get the style info. And here is the loss content. Create content loss, session model, blah. We have the loss content, loss style, and loss denoise. So what we are doing here, we are building the structure of the model. That's what we did.
You may see, as you see this, you're going to see words like graphs and stuff, and that's just based on the different types of frameworks that you're using. Like TensorFlow, like I think it creates a graph first and then runs, and then PyTorch has like a different way of like. My point is the way this runs changes based on what framework you're using, like what backend, like TensorFlow, PyTorch, or Cafe or whatnot. They all have their own unique methods of doing it, which have their pros and cons. And that's one of the reasons why we use Keras, because changing between them is much easier than.
No, that's why the TensorFlow 2.0, this is TensorFlow 1, which is very good, of course. But this structure, basically, what I'm doing, instead of whenever you get into your computer and runs every single line and see if it works or not, in TensorFlow, you have to create everything, and then you run. And unless we have a genius here, you're going to make a mistake. And then you're going to say, oh my God, where I made it? And then you have to identify where. So now you have in TensorFlow 2.0, you have this the eager mode where you can run line by line when you are constructing. So that's the bit of the 2.0.
Is it out?
Yes, it is. I don't know, 1 month, 2 months.
The news, I just saw it like a couple weeks ago, so I'm not on that.
Yes.
Some of the code is different than the one on Sirage's
Yeah.
GitHub, yeah.
It's because I changed some things. I was playing with this, but the idea is, well, I downloaded the Siraj code, and of course I played a little bit with. Now everything that and that's the point of the class. Everything that I use for almost everything, I grab some source on GitHub, and I adapt to some real situation that I'm facing. Almost everything. Only once I had to create something because it didn't exist.
How do you typically search for the models in GitHub?
How do I?
Yeah.
How do I search for the
Yeah,
models?
what are the keywords or how do you do
The keywords are, what do you want to do? The answer of this question. So I want to make a image prediction. Put image prediction. Then you put the language that you would like. For example, Python, in my case. And it's going to appear a lot of code. And then I go through, I select a few of them. I see the ones that I think that it seems to be good, well explained. And based on that, I start doing. There's another thing, Google it, because probably there's going to be some discussion on which model is going to be better for image prediction. VGG16 or da-da-da. And then there's going to be a discussion that's, okay, so I'm looking for VGG16 Python code for image prediction. And then you have there. Now, why do you need to know how to create the algorithm? That's our next class, and that's more or less what we are doing here. Because if you don't understand what you're doing, you're not going to be able to create a good algorithm. What you're going to grab from GitHub is a framework, is 80% ready. 80% ready. But you need to understand every single step. What if I change the loss function, instead of squared errors, I use absolute values? what does that change in my output? Is this more suitable for my output or not? Activation functions. What if I change the activation function here? What is going to be the output? What is going to change? This is the question that you have to be able to answer. Yeah.
Can we run the code like we did in the NLP class?
Right now?
This code, yeah.
Just while he's running that, is on more even like before you even choose the activation function stuff, in a fundamental layer, like how are you physically reading the data? They might have a completely different size of data, so you need to change that in the beginning layers. And based if they're using a different framework or something, like the channels, like if it's a red, green, blue, or if it's just a black and white image, that needs to be changed. So fundamental understanding of how, like step by step, how the data is put in, how the data is processed, and how you're using, running the model. Those kind of things need to be very, very solid in order to actually get it to work in the first place before you copy it itself. And then once you get it working, then obviously, like he said, fix the activation functions, change the number of layers or whatnot. So to purely get it to work, you completely need to understand how the data is processed and how it's loaded into the model.
Okay. No. So basically, let's we have here. So we have the losses. We define the losses in our model graph, and those guys here are the things that we're going to adjust for the content, style, and the noise. Session.run. So here we initializing what we're going to change on based on the loss functions, and here is what we're going to the updates, the things that are going to update the weights. Finally, to finish this, we have here the loss combined. Again, remember that the final loss is a combination of the losses. The gradient is this guy here. So model input is going to show the activation functions that is going to calculate the partial derivatives. The loss combined is the value that you're going to adjust the weights to try to diminish that value. So that's what we're calling the gradient. Run list is everything that we're going to run. And we're going to create something called mixed image that we're going to disclose in the end. And now this is the part that we run. Let me go through here. So and we're printing stuff. Yes, please.
Sorry. If this seems way more complicated than what we did in the NLP class or what we did in the classes before, because this is exactly what's going on underneath the hood for Keras and stuff like that. So we've breezed over, we never really went this into depth into running the session, getting the weight set, putting in a loss array list of losses, because that does it automatically. But in order to get, a more solid grip, it's really important to understand what goes on with TensorFlow itself. If you want to be a master expert or something, you can obviously build it from scratch without using TensorFlow. But
we're going to teach.
Yeah, but it's at least really important to understand this part, so you can at least know what you're talking about. You can just say, oh yeah, model does save model.fit, but what's actually going on? Why is this working the way it's working? So it's kind of important to understand this part a bit, a lot.
Yes. So let me. Okay, now I'm going to use that ugly LinkedIn picture. I just uploaded it. Now I use the load image function to do that we define it here. For those who cloned the code, there's a folder called images. You just put your image there, any image that you want. I don't know, your spouse, kids, etc. Put the style there that you want as well, and just change these names here. So you have the folder images, you just change the name for the name of the picture, the name of the style that you're going to use, and then you're going to be able to play with your family.
There are multiple styles available? Or?
No, you can choose the style actually. You put any.
It's an image.
It's an image.
Okay.
It's
just a picture.
If I take a picture of that red carpet thing, then I take the style of the red carpet. So based on the images. So it's not.
Just another image.
It's just another. It's not like a specific style. Like, it's just another image.
Okay, so running, da-da-da. Okay. Okay, it's running. Now,
This is what we saw earlier. The layers, the layers that we're using for style and layer for content.
okay, so this is the ugly picture. This is the style that we're going to use, and this is the mixed picture. Iteration 0. Now the 10th iteration. So much better. 20. Da-da-da. So an interesting thing to notice here is that this image here has much more style than this one. You can see
Yeah.
the contours more here.
Yeah.
But it looks the same. So I want to only run for, instead of, I think we use 10 nipples here. I would use, 120 interactions.
Yeah, 20. But once you could stop in the last one, I just wanted to make something.
Right. That's the last.
Could you scroll up just a bit? On here? You just okay. So the reason why it's like yellow and blue as compared to like white or light blue, like for us it seems like the style itself, but if you look at it, it kind of sticks out with the rest. And these would be some of the features that are extracted by the convolutional neural network when we're trying to do the style extractor. So the only things that are shared between all the layers is this like weird like yellow and blue mesh. That's what's shared through the layers after these hills are extracted, the sky swirly thing. So this kind of color combination is what's like, if you, I don't know, it seems really weird to explain this, but if you split the image up into like n number of layers, this is what this mesh of yellow and blue is what is between each one, which is shared across all of these layers while extracting the style. That's the only reason why you don't see white or dark blue, but rather you see this yellow and sea blue kind of thing. It's what's shared.
An interesting thing to do, if you want to do that, remember that the style, we multiplied the image by its transpose. And we did that for our red, green, and blue. We have 3 layers behind. So this, whenever you're multiplying, you're grabbing this mixture. Now, what we could do is, instead of multiplying like that, we could put everything white until here and colored here in the transpose matrix and see what grabs, which kind of style it would grab, what would happen. We can play with this in a lot of ways, in a lot of different ways. And that's the coolness of this. You can mix, you can grab 2 images. Look, an image for a computer is just a matrix with numbers. You just change the numbers. See what happens. Okay, we have 20 minutes. Oh my God, we have a lot. Let me do this. Instead of 10, let me take. The content, I put it 1, let me put it 100. Let's see what's going to change. Look, that's the interesting part here, and that's the hyperparameter that you can play with. What I did now, the previous model, it had only 1 as the content weight. Now I said, okay, let's put 100 and see what happens. This means that the content image is going to be much more important than the style image. So
Wow.
and you can
Big
see that
difference. Yeah, big difference.
only small points of
Yeah.
Just dots over
yellow,
here.
green stuff happening,
It's like barely changing.
right?
Yeah, yeah, it's cool.
Now imagine this is hard to build, but imagine that you have a map and then you scroll down the weight that you want for content, the weight that you want for style, and then the image changes. Of course, that we are not there with this model because it takes a few minutes. But this is something that we can embed, right?
The 100 is like, what is 100? Is it out of something or it's
Well,
not percentage?
The weight
Is it one,
Remember-
1 to 100? Is it a 1 to 100?
Remember that we created a loss function for the content image, a loss function for the style image, right?
Yeah.
And then I created something that's 2 weights, one for each loss function. The 100 is much larger than 10. This is the value that is going to multiply the loss function. This means that
Shouldn't the total of the 2 weights be equal to 100 or something so that we can balance it?
but the content, remember that I select a layer for content. So that loss function, the loss times 100 is coming from that layer. So what the algorithm does is he pays a lot of attention to that layer. He updates the weights in that layer so he can diminishes the total loss. And he doesn't pay a lot of attention to the style layers because the weight is so simply huge. Now, when he does that, what he's actually doing is grabbing the information that comes, the final model grabs the information, pays more attention to the information of this layer. That is the context.
What is the denoise? DENOISE?
It's a third noise that we added.
It's for the loss function for the mixed image. It's up above.
What does it mean?
Like we're just going through it.
It's here.
Right here.
Oh, surprise noise in mixed chain. We're generating. Oh, okay.
It's a loss function for the mixed image.
It's what?
Yeah, I believe it's a loss function for the mixed image. When you're combining both these images, you need to reduce the loss for this denoise loss. So that's why I think that it is.
I don't know.
It's a random thing
It's
that
a
you
math
put there just to.
Step number
Denoise.
5.
It's D.
What is this
denoise,
step number
not
5?
denoise. It's not like a name.
It's here,
It's
the
like
line of
reduce
code, yeah.
denoise.
Oh,
Step
I
three,
see.
step
DE
5.
is from, from the Latin. Okay, got it.
The
Here's
line-
step 3.
no, the
Destroy.
fourth-
I don't know. It's like denoise. Reduce the noise.
D is
Fifth line of code.
Ah. Okay. Step 5.
Degenerate.
Yeah, exactly. Degenerate. It's the same thing.
Yes.
It's different.
Yeah, it's very different. It's got one line here.
Ah, okay.
That's
I can upload this.
okay.
Let me see. I said that I was going to just say something in the end. I forgot what it was. Questions?
Yeah, so for a 2-part question, how many layers does this model have?
16.
16. And we're changing, we're pulling in the content from, I think, the 2nd layer and the style from the 5th or
The
something.
4th layer, yes, but yes.
Something like that. First of all, how do we know that content within layer 2 and the style in 5?
You define.
You choose a layer.
You choose.
You choose what layer that you want to extract the content, and you choose what layers you want to extract the style from.
There is a look again. Like I believe a little bit on this big number thing. So a lot of people doing a lot of this, and sometimes I hear something. But there is a thumb rule regarding image recognition, where the previous layers are there, captures the more abrupt features, just like contours, whilst the last layers captures details, fragments, etc.
And
So
because style is a broader brush stroke. We know that it's a later layer.
You need various layers for style, but like as you said, it's based on the features that are extracted as you're going through the network. Like if you're like choosing something a layer like farther and farther to the end, you're gonna get like really fine details kind of thing. Like maybe if you're looking at a cat's whiskers instead of getting the cat, I mean, if you're looking at a cat instead of getting like a cat's face, it's whiskers, like it's going to be really detailed. Like only certain, like based on what we talked last time, we're trying to get an abstraction of each one by doing the max pooling and stuff like that, right? Like in order to abstract each and every layer to get like, you know, a broader and broader feature range. The more detailed, like you get a higher detail layer, the deeper you are into the model, and versus very coarse features earlier are into the model.
And it makes sense that for you to choose the previous layers for content, because they are already trained to capture this kind of information that you want.
Yeah.
So if you were to choose a last layer for content, it would work, but it would need much more training, so much more time, but it would work. Yes.
So here you said you already use the models already been trained to extract content.
Yes.
Okay, so that step is already been taken care of.
Yes. So they used, I don't know how many million images, and actually this algorithm, I might be wrong, but please double check, but this algorithm can differentiate the content in an image, 10,000 different contents. So it has been trained a lot. What we're doing is just
So in general, so if image recognition is still kind of what we call the context dependent. So when you train particular model, so basically say, so someone the development model has to have knowledge in terms of subject. So say different. Let's say for this one kind of you have to extract the human from the image, right? Then if you apply it under other areas, something like say
Formula One cars.
Yeah, so I'm working on some like humor samples. Basically, say each different type of humor, the image really different way. So then you have to train certain type of especially train the model for that type.
There's the best way to go with this. What we did here was we only have 2 images. Look at the beauty of this. We only have 2 images. We don't have a training set.
Yes, that's correct.
If you do have a training set, the correct way to do that is to have 16 layers, right? What you're going to do is to reinitialize the last layer's weights, and then you train on your data. This one is style transfer. This methodology that I'm saying is transfer learning. We can even, yes, but that's what you are looking for. There are a bunch of videos, tutorials on that. If you want some help with that, I can help you, definitely.
Is that picture, is that accurate? I mean, it seems, based on what you said, what I heard was that for the content, you have several layers, and then on an independent path, you have the style set of layers, and then at the end, they're merged.
No.
Yeah.
No, that's not it. But yes, I'm going to choose some layers to.
But that has everything going into the same layer.
Okay. Okay, this is just something. The way that we define, so you can see, is it's a. Let me show you this. I haven't shown you that. I should have. We decided to have 1 layer responsible for content and 13 layers responsible for style. But notice that the layer for contents is also in the layer of style. So, and the loss function that we are actually multiplying the gradient, etc., is a combined loss function. It's not like we train one, we train the other, and then we merge. No. What happens is, and that's why I changed the weight to 100, is that the algorithm, the gradient descent, is going to understand that the majority of the loss comes from a certain place. And then he's going to put more effort in that place. And this is why we're going to get this.
What you were describing earlier is similar to like again, like how you have like a generator network which is generating these images, and the adversarial network is trying to prove that it's false. Like that's where they would actually come together. That's more similar to what you're saying. But over here, I know this is kind of a messy drawing, but each line represents a layer, and this is like the specific content layer, and the layers that you can see like in the VGG16 model, like everything and whatever else is selected. These become the style layers. So you're not two separate things which are merging in together, but rather like one sequential model, and using a particular layer for content and the rest of the layers for
Then if you go to that, it says your first 4 boxes
Oh yeah.
are styled exclusively.
No, they're
And
comfortable.
then at the 5th box, it's using both. And then from forever and ever and
Yes. But you understand that the way that the algorithm was set is you're going to know where you have to tweak to diminish the loss function. That's the whole point. I think that's the whole point. If we were to have interpolation or over in the first layers, let's say that the content would be the first 4. The algorithm, whenever I put a lot of weights, are going to spread the attention into the 4 layers, the first 4 layers. Now this is how we put it. Guys, questions? Last question?
About this entire thing.
All right, I see that everybody is excited. Wait, just one last question, Have you learned something today?
Oh, yes. Oh, yes,
Right.
absolutely.
you share the score.
I will share the code. Now, question for next class. What do you want? Hands-on, another heavy algorithm? What would you prefer?
Interesting use case, like trying to fool a convolutional neural network, make it classify something
That's
that it's
nice.
completely not. Like analyzing security risks with these neural networks. That's something.
I think that the first question would be hands-on or not hands-on, right?
Theoretical.
Okay, so again, hands-on, raise your hands. Well, it's 50-50, not hands-on, and not 50-50. There are a lot of people who are,
You didn't vote.
those who didn't vote. Looks like a American election, right? Okay, so hands-on, we're going to do something, we're going to prepare something hands-on. Okay, tomorrow I'm going to send, oh, please, fill the, I don't know how to do that, the best way to get in touch with you regarding the project. Because I can send messages at the meetup, but I don't think that everybody looks into that. Is it better for me to send emails?
You can send a community email. Like there's an option on the meetup itself to send an email to all the members of the community.
Yes.
So I mean,
That's cool. No, but the goal is to look at the groups that are going to work on the.
oh yeah.
So we need to focus on. Oh, by the way, we have a Slack channel.
Oh yeah.
That's a very good question. I'm going to post on GitHub this Slack channel. And I think that the project manager is going to be responsible for getting in touch with the group.
All right.
Of course, that's the project manager job. And questions, anything?
Comments?
Comments?
Yeah, I've just got one comment. I know most of the people here are using Python, but as you were talking, I just got this running in R. If you're an R person.
In R?
With R, yeah. I did a style
Okay.
with
That's
R.
in shopping.
It was a pretty big
Yeah,
file,
okay.
half an hour. But I can show you if you want.
So you're doing that, but it's in all.
No, I'm not the
Okay,
expert.
I know
I'm
where it
just
is.
running code.
All right, thank you, guys.
All right. Does it say you have to make an appointment? You just go?
Do you want to access your file?
Getting a lot out of it.
No, it's just to say that it's I did that, yeah.
So,
Just send us a message.
yes. No, Joe is
I don't really know what it is.
My wife called me and said,
Yeah, no,
"Oh, is he out here at the gym?" I said, "Yeah, yeah." Then I sent me an email for that to come. Because I will say, a spring break was on?
Outside, like, 99%.